Hi kids, this video is on changing momentum in an open system. And forgive me here, I'm still getting over this voice situation, so I sound a little bit funny, but hopefully you can still tell what I'm saying. The goal of this lecture is to determine what variables are going to decide or determine how much an object's momentum changes, and hopefully we can eventually come up with an equation that will prove it. Okay, so 1726, Isaac Newton is sitting on a bench next to an apple tree and pondering life, the universe, and everything, and all of a sudden an apple falls from the tree. And he started thinking about the movement of that apple. So I want you to think about the movement of the apple. From the moment that before it drops until it's at rest on the ground, what's happening to that apple's momentum? So if you did a thorough job thinking about what was happening to the apple, you realize that there were 4 phases in that apple's motion. In the first phase, before the apple falls, it's at rest. It's got 0 momentum as it's sitting up on the tree. Second phase, as it's falling, that apple is speeding up as it falls. All objects that are falling speed up as they fall. That means it's got increasing negative momentum. Third phase is probably the trickiest. That object has a big negative momentum right before it hits the ground. It's got the most negative momentum it'll ever have. It's fastest right before it hits the ground. But then there's a small amount of time where that apple has to slow down to a stop, right as it's touching the ground. So as the apple is touching the ground, it starts slowing down very quickly in the negative direction until it hits 0. That phase has decreasing negative momentum. Then, once it finally comes to a rest on the ground, it's just sitting there, which means it has no velocity and no momentum. So what kind of system makes sense to think about the momentum of this apple? Is it a closed system where momentum's conserved, or an open system where it's not conserved? Hopefully you guys realize that since apples has such a dramatically changing momentum, it's really not going to be easy to handle this with a closed system. We don't know what the other objects are. We can't really track those other objects terribly well. The entire Earth is one of those objects, and that's awkward. So it's really going to be easier to handle this apple as an open system and think about the changing momentum just with the apple instead of the entire system. So let's draw this momentum system as an open system. Start off with your apple at rest. Okay. Then we're going to take that apple and we're going to add some negative momentum to that apple. That's when the apple is going to be falling. And when you go from no momentum to negative momentum, your velocity is changing. In this case, it's speeding up. Negative momentum means we're moving downwards, but because we had 0 momentum and now we have more, even though it's negative, this apple's actually speeding up. So in the third system, we actually have that apple and it's currently moving downwards. It's moving downwards because of that negative momentum that we added in the second system. And then we're going to take some of that momentum back out. This is the phase where the apple's touching the ground. So as that apple touches the ground and slows to a stop again, we're going to take the momentum back out of that system, away from the apple, and go somewhere else. Velocity is changing again in this situation because we have momentum that is either going in or out of the system. In this case, that apple happens to be slowing down because the momentum, we're adding positive momentum to this apple, and it started with negative momentum. So that brings us closer and closer and closer to 0 until we finally hit the apple at rest. Once we pulled all the same amount of positive momentum away from that apple as it gained in the second scenario, we end up getting that fourth phase where the apple is at rest again. When you're dealing with an open system, it's always important to ask yourself the question, why is that object's momentum changing? Okay, because we know momentum in the universe is conserved. So if one object's momentum is changing, we've got to think a little bit about where it came from. And in the case of open systems, the reason why an object's momentum is changing is because there's some kind of external force acting on the apple. If you watch that force video that we posted in the last unit, you know that a force is just a push or a pull. So the idea is that something from outside the system is pushing or pulling on the apple during phases 2 and phases 3. A little bit of definition that I probably should have given you earlier, but anyways, we're doing it now. When I say external, that's a force from an object outside the system. External forces cause the momentum of the objects in the system to change. So that apple is being pushed and pulled on by the earth or the floor, Those are things that we don't have in the system, so all those forces are external. In our last unit, we had plenty of forces. We had lots of objects exploding and pushing off of each other, etc. But all of those forces were internal because all the objects involved were inside the system. For example, those carts, when they had the kids sitting on the carts, we watched that video, right? They're exerting forces. They're pushing on each other. But the kids and the carts are all inside the system. So that means those forces are internal forces. And when you have internal forces, the overall momentum of the system is constant. It doesn't change. So in my closed system, we can have forces. They're just internal. In my open system, the forces are external from other objects. So the most interesting two phases of our open system diagrams we made earlier were the phases where the momentum of the apple was changing. So let's take a little bit of a closer look at those intervals where my momentum is changing. Anytime we have a changing momentum, there must be an external force. Okay. In this case, in the first scenario where the apple was sitting on the tree and then it started falling downwards and speeding up, the external force is actually Earth's gravity. That force is, I'm labeling it as a negative force, and the reason I'm calling it negative is because it's pulling downward on the apple, and it's an external force because Earth isn't in my system. In the second or the third phase, we had changing momentum again, but this time we have a positive change in momentum. Positive change in momentum is going to be caused by a positive force, some sort of force pushing upwards on that apple. If you think about what's pushing upwards on the apple, bringing it to a stop, hopefully it would make sense to you that that positive force is the force from the ground. It's the ground actually pushing upwards on the apple and holding it up. The next question is that force the only variable that causes this object's momentum to change? Is the force the only thing that matters? And to answer this question, think about what would be true if the force was the only variable that mattered. If the force is the only relevant variable, then a little force could only ever cause a small change in momentum. So if an object can't push very hard, that means it can never make a different object's momentum change by a lot. And a large object could only ever, a large force could only ever cause a large change in momentum. If force is not the only variable that matters, then a small force could cause a large change in momentum in certain circumstances and vice versa. This is worth just taking a couple seconds to think about. Can you guys think about any situations where a small amount of force can cause an object's momentum to change by a whole lot? So to me, the scenario that kind of proves that force can't be the only variable that affects momentum, change in momentum, is the slow and steady wins the race idea. Think about a tiny ant pushing a tiny ball. Now, at the beginning, obviously, this ball is going to be going very slowly because the ant's pretty weak. It can't push with very much force. But if you allow that ant to keep pushing over a very long period of time, that ball is just going to get faster and faster and faster and faster. And if you let it keep on pushing, eventually that ball could be going faster than a bullet, be faster than a train, faster than an airplane. Eventually that tiny little ball could have an enormous amount of momentum if you just allow that ant to keep pushing with its very small force for a very, very long period of time. Okay, so we can use the two variables that we've talked about that make a difference in the change in momentum of an object to come up with an equation for change in momentum. And we've already talked about how the change in momentum depends on two things. It depends on the amount of force that we're exerting on an object, the external force, and it depends on the amount of time that we push on that object. So if we exert a large force, a large external force, do you think that will make the object's momentum change by a lot or a little? Hopefully it makes sense to you guys that the harder we push on an object, the more we're expecting its momentum to change. That's a direct relationship. Now, if we push on an object for a really long period of time, so we keep pushing on it for a long time, will that make its momentum change by a lot or not very much? Hopefully it makes sense to you that that also will make it change by a lot. So delta t, or the amount of time we push on an object, has another direct relationship with delta p, or change in momentum. Now we've got our two relationships, we can combine those guys into a single equation. The equation would look like this: F net delta t equals delta p, right? Two direct relationships is equal to delta p. Often that equation is modified a little bit, expanded a little bit, because we know that p is equal to mv. And so I can replace the p with an mv in my equation. But let's think about the change part. Does mass usually change or does velocity usually change? Typically for most objects, their mass is staying the same. And so delta p can also be calculated as m delta v, because that shows that it's the velocity that usually is changing when we're exerting a force on an object. It's not usually causing the object's mass to change. So this equation can be rewritten as follows. F net delta t equals m delta v. Some kids have called this the fat mav equation. That delta sign kind of looks like an A. So F delta t equals m delta v, or fat mav if you want to think of it that way. So this is the last slide in this video. We're going to be using these equations more in the coming days and weeks. Thank you.